Chapter 2, Moving Pulse Systems. There are three categories of pulse system and we will consider each in turn. These are dry pulse systems, energy tapping pulse systems and gravity-free energy pulsing systems. Here we will look at systems where an electrical pulse is used to cause the device to operate by creating a temporary magnetic field caused by electric current flowing through a coil or electromagnet as it is often called. Many of these systems are rather subtle in the way that they operate. One very well-known example of this is the motor/generator of Robert Adams. The late Robert Adams, an electrical engineer of New Zealand, designed and built several varieties of electric motor using permanent magnets on the rotor and pulsed electromagnets on the frame of the motor, called the stator because it does not move. He found that if they were configured correctly, then the output from his motors exceeded their input power by a large margin, 800%. The diagram of his motor intended to show the basic operating principle is shown here. If a motor is built like this, then it will most certainly work, but it will never reach 100% efficiency, let alone exceeding the 100% mark. It is only with a specific configuration, which is hardly ever publicized, that high performance figures can be achieved. While Robert has shown several different configurations, in order to avoid confusion I will describe and explain just one of them. I am indebted to several of Robert's friends and colleagues for the following information, and I should like to express my thanks to them for their help and support in bringing you this information. First and foremost, high performance can only be achieved with the clever use of power collection coils. These coils need to be positioned accurately and their power collection restricted to just a very short arc of operation by connecting them to, and disconnecting them from, the output circuit at just the right instant, so that the back EMF generated when the current draw stops, actually contributes to the drive of the rotor, speeding it on its way and raising the overall efficiency of the motor/generator as a whole. Next, the shape of the magnets used is important, as the length to width proportion of the magnet alters the pattern of its magnetic fields. In direct opposition to the diagram shown above, the magnets need to be much longer than their width, or in the case of cylindrical magnets, much longer than their diameter. Further, a good deal of experimentation has shown that the size and shape of the electromagnets and pickup coils has a major influence on the performance. The cross-sectional area of the core of the pickup coils should be 4 times that of the cross-sectional area of the permanent magnets in the rotor. The reverse is true for the cores of the drive coils, as their cores should have a cross-sectional area of just 1/4 of the rotor magnet cross-sectional area. Another point which is almost never mentioned is the fact that big circuit gains will not be achieved unless the drive voltage is high. The minimum should be 48 volts, but the higher the voltage, the greater the energy gain, so voltages in the 120 volts, rectified US mains voltage, to 230 volts, rectified mains voltage elsewhere, should be considered. Neodymium magnets are not recommended for drive voltages under 120 volts. This is one of Robert's test circuits. Notice that the cores of the generator pickup coils are very much wider than the cores of the drive coils. Also notice the proportions of the magnets where the length is much greater than the width or diameter. The 4 generator windings are mounted on a single disc, allowing them to be moved through an angle to find the optimum operating position before being locked in position, and the 2 drive coils are mounted separately and held clear of the disc. Notice also that the power pickup coils are much wider compared to their length than the drive coils are. This is a practical feature which is explained in greater detail later. The DC input is shown passing through Robert's custom-made contactor switch, which is mounted directly on the shaft of the motor/generator. This is a mechanical switch which allows an adjustable on/off ratio, which is known as the mark/space ratio, or, if the on period is of particular interest, the duty cycle. Robert Adams indicates that when the motor is running and has been adjusted to its optimum performance, then the mark/space ratio should be adjusted to minimize the on period and ideally get it down to about 25%, so that for 3/4 of the time, the input power is actually switched off. There are various ways of achieving this switching while still having a very sharp turn on and turn off of the power. Robert considered mechanical switching of the drive current to be a very good option, although he was not opposed to using the contact to power a transistor to do the actual switching and so reduce the current through the mechanical contacts by a major factor. His reasons for his preference for mechanical switching are that it gives very sharp switching, needs no electrical power to make it operate, and it allows current to flow in both directions. The current flow in two directions is important because Robert produced various ways of getting the motor to feed current back into the driving battery, allowing it to drive the motor for long periods without lowering its voltage hardly at all. His preferred method of switching is shown here. This switching gear operates as follows: the timing disc is bolted securely to the drive shaft of the motor and its position is set so that the electrical switch on occurs when the rotor magnet is exactly aligned with the drive coil core. Adjustment of that timing is done by loosening the locking nut, rotating the disc very slightly and clamping the disc in position again. A spring washer is used to keep the assembly tight when the device is running. The disc has a star-shaped piece of copper sheet set into its surface and two silver-tipped, copper arm brushes slide across the surface of the copper star. One of these two brushes is fixed in position and slides across the copper star near the drive shaft, making a permanent electrical connection to it. The second brush slides alternatively on the non-conducting surface of the disc and then over the conducting arm of the copper. The second brush is mounted so that its position can be adjusted and, because the copper arms taper, that alters the ratio of the on time to the off time. The actual switching is achieved by current flowing through the first brush, through the copper arm and then through the second brush. The brush arms shown in the diagram above rely on the springiness of the copper arm to make a good brush-to-copper electrical connection. It might be preferred to use a rigid brush arm, pivot it and use a spring to ensure a very good contact between the brush and the copper star at all times. The adjustment of the on-to-off time, or mark/space ratio or duty cycle as the technical people describe it, could perhaps do with some description. If the movable brush is positioned near the center of the disc, then, because of the tapering of the copper arms, the part of the non-conducting disc that it slides over is shorter and the part of the conducting copper arm with which it connects is longer. As the two sliding paths are about the same length, the current is on for about the same length as it is off, giving a mark/space ratio of about 50% as shown here. If, instead, the movable brush is positioned near the outside edge of the disc, then because of the tapering of the copper arm, the on path is shorter and the non-conducting off path is very much longer, being about 3 times as long as the on path, giving a mark/space ratio of about 25%. As the movable brush can be positioned anywhere between these two extremes, the mark/space ratio can be set to any value from 25% to 50%. The two brushes can be on the same side of the drive shaft or on opposite sides as shown. One important feature is that the brushes touch in a position where the disc surface is always moving directly away from the brush mounting, causing any drag to be directly along the arm and giving no sideways loading on the brush. The diameter of the device is usually 1 inch, 25 mm, or less. You will also notice that the output is switched, although the diagram does not give any indication of how or when that switching takes place. You will notice that the diagram has angles marked on it for the optimum positioning of the pickup coils. Well, an Adams motor builder with a forum ID of May Mariety, who achieved a coefficient of performance of 1223, found that the optimum switching for his motor is on at 42 degrees and off at 44.7 degrees. That tiny 2.7 degree part of the rotor turn gives a substantial power output, and cutting the output current off at that point causes the back EMF of the coils to give the rotor a substantial additional boost on its way. His input power is 27.6 watts and the output power is 33.78 kilowatts. Now for some practical details. It is suggested that a good length for the power pickup coils can be determined by using the paper clip test. This is done by taking one of the permanent magnets used in the rotor, and measuring the distance at which that magnet just begins to lift one end of a 32 mm, 1.25 inch, paper clip off the table. The optimum length of each coil from end to end is exactly the same as the distance at which the paper clip starts to lift. The core material used in the electromagnets can be of various different types, including advanced materials and alloys such as Simalloy or Medglass. The power pickup coil proportions are important as an electromagnet becomes less and less effective as its length increases, and eventually, the part furthest from the active end can actually be a hindrance to the effective operation. A good coil shape is one which you would not expect, with the coil width being, perhaps 50% greater than the coil length. Contrary to what you would expect, the device draws in energy from the local environment better if the end of the pickup coil farthest from the rotor is left unaffected by any other part of the device, and the same applies to the magnet facing it. That is, the coil should have the rotor at one end and nothing at the other end, that is, no second rotor behind the coil. The speed at which the voltage is applied to, and removed from, the coils is very important. With very sharp voltage rises and falls, additional energy is drawn from the surrounding environmental energy field. If using transistor switching, then the IRF3205 FET has been found to be very good, and a suitable driver for the FET is the MC34151. If using a Hall effect semiconductor to synchronize the timing, say the UGN3503U, which is very reliable, then the life of the Hall effect device is much improved if it is provided with a 470 ohm resistor between it and the positive supply line, and a similar 470 ohm resistor between it and the negative line. These resistors in series with the Hall effect device effectively float it and protect it from supply line spikes. Here, two electromagnets are driven by the battery via Robert's 4-arm commutator, which is mounted on the rotor shaft. Some of the recommendations given by Robert are the opposite of what you would expect. For example, he says that a single rotor construction tends to be more electrically efficient than one where several rotors are mounted on a single shaft. Robert is against the use of reed switches, and he recommends making one of his commutators. At one stage, Robert recommended the use of standard transformer shims for constructing the cores of the electromagnets. This has the advantage that matching bobbins for holding the coil windings are readily available and can still be used for pickup coils. Later on, Robert swung towards the use of solid cores from the old PO Series 3000 telephone relays and eventually said that electromagnet cores should be solid iron. The diagrams presented by Robert show the magnets located on the rim of the rotor and pointing outwards. If this is done, then it is essential that the magnets in the rotor are firmly attached on at least 5 of their 6 faces, and the possibility of using a ring of non-magnetic material such as duct tape around the outside should be considered. That style of construction also lends itself to streamlining the rotor by having a completely solid construction, although it might be remarked that the motor would run better and more quietly if it were enclosed in a box which had the air pumped out of it. If that is done, then there will be no air resistance, and because sound can't pass through a vacuum, quieter operation is bound to result. While this may sound a bit complicated, there is no reason why it should be. All that is needed is 2 discs and 1 central disc, which is the thickness of the magnets, with slots cut in it, the exact size of the magnets. The assembly starts with the lower disc, magnets and central disc. These are glued together, probably with epoxy resin, and that holds the magnets securely on 4 faces as shown here. Here, the magnets are attached on the lower face, the right and left faces, and the unused pole face, and when the upper disc is attached, the upper faces are also secured, and there is the minimum of air turbulence when the rotor spins. There is a sweet spot for the positioning of the power pickup coils, and it will usually be found that this is 2 or 3 mm away from the rotor. If that is the case, then there will be room for an outer band of duct tape on the rim of the rotor to provide additional protection against the failure of the magnet attachment method. High-power versions of the motor/generator need to be enclosed in a metal box which is earthed, as they are quite capable of generating a substantial amount of high-frequency waves which can damage equipment such as oscilloscopes and create TV reception interference. There would probably be an improvement in performance as well as a reduction in sound if the box was airtight and had the air pumped out of it. If that is done, then there will be no air resistance as the rotor spins, and since sound does not pass through a vacuum, quieter operation is possible. Experienced rotor builders do not like the radial magnet style of construction because of the stresses on the magnet attachments if high rotational speeds are reached. It should not need to be said, but it is obviously a major requirement to keep your hands well away from the rotor when the motor is running, as it is perfectly possible to be injured by the high-speed movement if you are careless. Please remember that this presentation must not be considered to be a recommendation that you build or use any device of this nature, and it must be stressed that this text, in common with the entire contents of this ebook, is intended to be for information purposes only, and no representations or warranties are implied by this presentation. Should you decide to construct, test or use any device, then you do so entirely at your own risk, and no liability attaches to anybody else if you sustain any kind of injury or property damage as a result of your own actions. Because of the mechanical stresses caused during rotation, some experienced constructors feel that the magnets should be embedded in the rotor as shown here, where they are kept well clear of the rim of a rotor which is made from a tough material. This is so that the outer strip of the material prevents the magnets breaking loose and becoming dangerous high-speed projectiles, which at best would destroy the electromagnets and at worst could injure someone quite badly. It needs to be remembered that the proportions of the magnets are for the magnet length to be more than the diameter, so in cases like this where circular magnet faces are to be used, the magnets will be cylindrical. And the rotor needs to have a significant thickness, which will depend on the magnets which are available locally. The magnets should be a tight push fit in their holes and securely glued in place. Robert Adams has used this construction style as well. However, if an arrangement like this is used, then there will be a substantial sideways pull on the rotor as it reaches the electromagnet core, tending to pull the magnets out of the rotor. It is important that the rotor should be perfectly balanced and have the minimum amount of bearing friction possible. This calls for precision construction and either roller or ball bearings. The construction style shown above has the distinct advantage that it has an open end to both the magnet and the coils, and this is believed to facilitate the inflow of environmental energy into the device. It may be my ignorance showing here, but I have a problem with this version. The difficulty as I see it is that the magnet/core pull and the subsequent drive thrust when the coil is powered, form a turning couple as they both try to rotate the axle in the same direction. This places a substantial loading on the axle bearings, usually amplified by the radius of the rotor being greater than the distance from the rotor to the axle bearings. This load will be in the tens of kilograms range and will be applied and reversed perhaps 40 times per second. To me, that appears like a vibration load and is directly opposed to the perfectly balanced rotor operation being sought. The radial magnet arrangement generally shown by Robert Adams does not have any of this kind of loading at all, because the coils are exactly opposite each other and their loads cancel each other out exactly. The choice is, of course, up to the builder and his assessment of the advantages and disadvantages of the different styles of construction. When getting ball race bearings for an application like this, please be aware that closed bearings such as these are not suitable as supplied. This is because this type of bearing is usually packed with dense grease which completely destroys its free motion, making it worse as a bearing than a simple hole and shaft arrangement. However, in spite of this, the closed or sealed bearing is popular as the magnets tend to attract dirt and dust, and if the device is not enclosed in a steel box as is necessary for the high-power versions, then having the seal is considered to be an advantage. The way to deal with the grease packing is to soak the bearing in an isopropyl solvent cleaner to remove the manufacturer's grease, and then, when it has dried out, lubricate the bearing with 2 drops of a high-quality thin oil. If it is intended to house the motor/generator in an earthed, sealed steel box, then an alternative type of bearing which might be suitable is an open design like this. Especially if the air is removed from the box. Some constructors prefer to use ceramic bearings which are supposed to be immune to dirt. One supplier is http://www.bocabearings.com/main1.asbx $P=$docs$ID=16. But as with everything else, these choices have to be made by the builder and will be influenced by his opinions. I'm not sure where it came from, but here is a circuit diagram showing a transistor drive and the return of the back EMF of the drive coils to the driving power supply. Using this method, about 95% of the drive current can be returned, lowering the current draw enormously. The diode feeding the power back to the supply is a Schottky type because of its high-speed operation. It needs to be able to handle the peak pulse power and so should be one of the more robust types. What this circuit does not have is the very important switching on the output coil circuit. Another strange item is the way that the FET sensor is arranged with two sensors rather than one and with an additional battery. While it must be admitted that the current draw of the FET gate should be very low, there still does not seem to be much reason to have a second power supply. One other peculiarity in this diagram is the positioning of the drive coils. With them offset as shown, it has the effect of them being at an angle relative to the rotor magnets. It is not at all clear if this is an advanced operating technique or just poor drawing. I am inclined to assume the latter, although I have no evidence for this other than the circuit design and the low quality of the original drawing, which had to be improved considerably to arrive at the diagram shown above. The coil generator output should be fed into a capacitor before being passed to whatever equipment is to be powered by the device. This is because the energy is being drawn from the local environment and is not conventional energy. Storing it in a capacitor converts it to a more normal version of electrical power, a feature which has also been mentioned by Don Smith and by John Bedini, although their devices are quite different in operation. The DC resistance of the coil windings is an important factor. The overall resistance should be either 36 ohms or 72 ohms for a complete set of coils, whether they are drive coils or power pickup coils. Coils can be wired in parallel or in series/parallel. So, for 72 ohms with 4 coils, the DC resistance of each coil could be 18 ohms for series connected, 288 ohms for parallel connected, or 72 ohms for connection in series/parallel, where two pairs of coils in series are then wired in parallel. To help with assessing the wire diameter and length which you could use, here is a table of some of the common sizes in both American wire gauge and standard wire gauge. So far, we have not discussed the generation of the timing pulses. A popular choice for a timing system is to use a slotted disc mounted on the rotor axle and sensing the slots with an optical switch. The optical part of the switch is usually performed by UV transmission and reception, and as ultraviolet is not visible to the human eye, describing the switching mechanism as optical is not really correct. The actual sensing mechanism is very simple, as commercial devices are readily available for performing the task. The sensor housing contains both a UV LED to create the transmission beam, and a UV-dependent resistor to detect that transmitted beam. Here is an example of a neatly constructed timing mechanism made by Ron Pugh for his 6-magnet rotor assembly. This device happens to be one which is supplied by www.buyereamusements.com under their product code number, OP, 5490, 1432700. As the slotted disc rotates, one of the slots comes opposite the sensor and allows the UV beam to pass through to the sensor. That lowers the resistance of the sensor device, and that change is then used to trigger the drive pulse for whatever length of time the slot leaves the sensor clear. You will notice the balanced attachment method used by Ron to avoid having an unbalanced rotor assembly. There can be two timing discs, one for the drive pulses and one for switching the power pickup coils in and out of the circuit. The slots in the power pickup timing disc will be very narrow, as the switch on period is only about 2.7 degrees. For a 6-inch diameter disc where 360 degrees represents a circumference length of 18.85 inches, 478.78 mm, a 2.7 degree slot would be only 9/64 inch, 3.6 mm, wide. The arrangement for an axial magnet rotor setup could be like this. So to recap, The things which are necessary for getting an Adams motor output into the Sirius bracket are: 1. A performance of COP1 can only be achieved if there are power pickup coils. 2. The rotor magnets need to be longer than they are wide in order to ensure the correct magnetic field shape, and the rotor must be perfectly balanced and have bearings as low friction as possible. 3. The face area of the rotor magnets needs to be 4 times that of the drive coil cores and 1/4 the area of the core of the power pickup coils. This means that if they are circular, then the drive coil core diameter needs to be half the diameter of the magnet, and the magnet diameter needs to be half the diameter of the power pickup core. For example, if a circular rotor magnet is 10 mm across, then the drive core should be 5 mm across and the pickup core 20 mm across. 4. The drive voltage needs to be a minimum of 48 volts and preferably, a good deal higher than that. 5. Do not use neodymium magnets if the drive voltage is less than 120 volts. 6. The drive coils should not be pulsed until they are exactly aligned with the rotor magnets, even though this does not give the fastest rotor speed. 7. Each complete set of coils should have a DC resistance of either 36 ohms or 72 ohms, and definitely 72 ohms if the drive voltage is 120 volts or higher. 8. Collect the output power in large capacitors before using it to power equipment. It may also be possible to boost the output power further, by using the coil shorting technique shown in the section of this chapter on the rotoverter. If you want the original drawings and some explanation on the operation of the motor, then 2 publications from the late Robert Adams can be bought from www.nexusmagazine.com, where the prices are quoted in Australian dollars, making the books look much more expensive than they actually are. The website http://members.fortunecity.com/free-energy2000/adamsmotor.htm is a location for Adams motor enthusiasts and may have information which might be helpful. http://www.totallyamp.net/adams/index.html is a really impressive collection of well-informed practical material on building and using an Adams motor, with details of sensors and how they work, core materials and their performances, and how to locate the sweet spot. Very highly recommended website. Femax's Inertial Propulsion and Electrical Generation System. Femax Technologies have developed what they describe as their sustainable transportation system, which is based on their inertial propulsion generation wheel, which uses what they call 3D coaxial hybrid induction, CHI, in which coaxial refers to their combined radial axial technique, where drive is provided by a radial pulsed magnet system and power extraction is achieved using an axially orientated magnet/coil system. Taiwan inventor, Tajin, David, Chi, says that his company, Femax Technologies Incorporated, will be demonstrating their technology in September 2010 at an expo, after which they will allow interested and qualified parties to come to their premises for licensing discussions. Their device can take the place of the battery component of an electric vehicle, or it can be used to supplement and recharge a battery bank in the vehicle. At the September exhibition, they will allow visitors to ride their 2 kilowatt test car. David intends to put their test data on the internet. With a rotational input of 1 New Mexico at 500 RPM, a single inertial propulsion generation wheel can produce 1 kilowatt of axial generative power. David also said that a 150W output from his motor actually produces between 180 and 200 watts of mechanical output, while a 1500W output produces a mechanical output of 1800 to 2000 watts, 96 volts at 20 amps, as measured by a watt meter, speed meter, torque meter, and oscilloscopes. He says that these measurements were made by Michael Su, Vice President and Chief Technology Officer. Ceramic-based and carbon-based ultracapacitors are used to return some of the output power to the input in order to keep the machine running continuously without the need for a power supply when the engine is running and providing its output. When driving a vehicle powered by this device, the mechanical driving torque is provided via a continuously variable transmission. At this time, Femax technologies include have a 150 watt and a 2 kilowatt prototype which they plan to demonstrate in September 2010. He says that they generally run these prototypes for 8 hours each day in their lab. The central principle of the Femax Technologies Incorporated process is what they call CORAXIA, which stands for Combined Radial Axial Hybrid Induction, abbreviated to CHI, which is David's surname. They also call this the 3D coaxial hybrid induction system. They state that their electromagnetic 3D arrangement enables the wheel to have both radial flux propulsion and axial flux generation with just a single rotor and two separate stators. As the radial electric drive rotates, the mechanical energy due to the inertia of the wheel and the ground power transmission mechanism enables the wheels of a vehicle to generate electricity as they rotate. There are two videos showing the device generating electricity, located here. http://www.youtube.com/watch?v=w_lzhpzxxcq and http://www.youtube.com/watch?v=08ardr-fno0 http://www.youtube.com/watch-v=08ardr, fno0 here. Another application is where the electrical output from the device is being used to produce a hydrogen/oxygen gas mix from water using an underwater plasma arc. David says he is self-taught in this area. He has 3 patents, Taiwan patent M352472, M372891 and M382655, which are not in English. From his search of the patent index, the internet and YouTube, David said he has not yet seen a patent or experimental setup similar to what they have developed. This motor/generator is unusual in that it uses pulsed rotor drive on magnets mounted on the circumference of the rotor, and simultaneously, it picks up electrical energy from a coil/magnet arrangement mounted on the side faces of the rotor as shown here. The basic drive/generator unit can be replicated on a single shaft to give increased power, still without increased frictional losses between the drive and the power generation. It is unusual to see this technique used as it can be difficult to avoid interaction between the different magnetic fields. However, David has been entirely successful in doing this, and the arrangement has no transmission losses between the drive motor and the generator, as these are integral components of the system. This system is capable of driving a self-powered air conditioning unit, and a 5 kW proof of concept prototype is shown here. This device is also capable of driving electric lighting, and with a 5 kW output self-powered output, it can power most household needs. A typical washing machine has a 2.25 kW maximum electrical draw, as does the average tumble dryer. Most fan heaters are 3 kW or less when on full output. If a wind power generator is already in place, then using the mechanical power of the generator to spin the axle of one of these CHI generators results in a very high power electricity generation system. Contact, Tajan, David, CHI, Taiwan. Email, chitajan@gmail.com. Inquiries to Femax Technologies Incorporated, Michelle Chen, Manager of Marketing and Business Development. Tel, 886, 2, 2371, 5622. Email, michelle@phemax.com. The exhibition is at the 6th Taipei International Invention Show and Technomart. The exhibition website is at http://www.inventaipe.com.tw/en_us/index.html, and it runs from September 30, 2010 to October 3, 2010. At the Taipei World Trade Center, Exhibition Hall 1. Raymond Cromray's electrical generator. Where the objective is to produce electricity from a rotating magnetic field, there has always been a search for some method of either reducing, or eliminating altogether, the drag on the rotor when electric current is drawn from the generator. One design which claims to have very limited drag caused by current draw is the Cromray design. The main characteristics of this design are said to be 1. It has almost constant electrical power output even when the rotor speed is altered by as much as 35%. 2. It can continue to operate with its electrical output short-circuited, without heating the rotor or causing a braking effect. 3. The production efficiency, electrical output divided by the driving force, is high. 4. The frequency of its AC output power can be adjusted to that required by the equipment which it powers. 5. The rotor can be spun at any rate from 800 rpm to 1600 rpm. 6. The simple construction allows manufacturing costs to be about 30% less than other generators. 7. This generator is recommended for supplying power at or above the 1 kilowatt level. Here is the patent for this device. Patent US 3,374,376 March 19, 1968 Inventor, Raymond Cromray. Electric generator. My present invention relates to an electric generator which converts magnetic energy into electric energy using two components which can rotate relative to each other, i.e. a stator and a rotor, one having electromagnets or permanent magnets which induce a voltage in a winding which forms part of an output circuit mounted on the other component. Conventional generators of this type use a winding whose conductors form loops in different axial planes so that opposite parts of each loop pass through the field of each pole pair, twice per revolution. If the loops are open circuit, then no current flows in the winding and no reaction torque is developed, leaving the rotor free to turn at the maximum speed of its driving unit. As soon as the output winding is connected across a load or is short-circuited, the resulting current flow tends to retard the motion of the rotor to an extent which depends on the intensity of the current, and this makes it necessary to include compensating speed regulating devices if it is necessary to maintain a reasonably constant output voltage. Also, the variable reaction torque subjects the rotor and its transmission to considerable mechanical stresses and possible damage. It is therefore the general object of this invention to provide an electric generator which has none of the above disadvantages. Another object is to provide a generator whose rotor speed varies very little in speed between open circuit operation and current delivery operation. Another objective is to provide a generator whose output voltage is not greatly affected by fluctuations in its rotor speed. I have found that these objectives can be achieved by rotating an elongated ferromagnetic element, such as a bar-shaped soft iron armature, and a pair of pole pieces which create an air gap containing a magnetic field. Each of the outer extremities of the armature carries a winding. Ideally, these windings are connected in series, and these coils form part of a power output circuit used to drive a load. As the armature rotates relative to the air gap, the magnetic circuit is intermittently completed and the armature experiences periodic remagnetizations with successive reversals of polarity. When the output circuit is open, the mechanical energy applied to the rotor, less a small amount needed to overcome the friction of the rotating shaft, is absorbed by the work of magnetization, which in turn, is dissipated as heat. In actual practice, however, the resulting rise in temperature of the armature is hardly noticeable, particularly if the armature is part of the continuously air-cooled rotor assembly. When the output circuit is closed, part of this work is converted into electrical energy as the current flow through the winding opposes the magnetizing action of the field and increases the apparent magnetic reluctance of the armature, and so the speed of the generator remains substantially unchanged if the output circuit is open or closed. As the armature approaches its position of alignment with the gap, the constant magnetic field tends to accelerate the rotation of the armature, aiding the applied driving force. After the armature passes through the gap, there is a retarding effect. When the rotor picks up speed, the flywheel effect of its mass overcomes these fluctuations in the applied torque and a smooth rotation is experienced. In a practical embodiment of this invention, the magnetic flux path includes two axially spaced magnetic fields traversing the rotor axis and substantially at right angles to it. These fields are generated by respective pole pairs cooperating with two axially spaced armatures of the type already described. It is convenient to arrange these two armatures so that they lie in a common axial plane, and similarly, the two field-producing pole pairs also lie in a single plane. The armatures should be laminated to minimize eddy currents, so they are made of highly permeable, typically, soft iron, foils whose principal dimension is perpendicular to the rotor axis. The foils can be held together by rivets or any other suitable method. If the ferromagnetic elements are part of the rotor, then the output circuit will include the usual current collecting means, such as slip rings or commutator segments, depending on whether AC or DC current output is desired. The source of coercive force in the stator includes, advantageously, a pair of oppositely positioned, yoke-shaped magnets of the permanent or electrically energized type, whose extremities constitute the pole pieces mentioned above. If electromagnets are used in the magnetic circuit, then they may be energized by an external source or by direct current from the output circuit of the generator itself. I have found that the terminal voltage of the output circuit does not vary proportionately to the rotor speed as might be expected, but instead, it drops at a considerably slower rate with decreasing rotor speed. So, in a particular tested unit, this voltage fell to only about half its original value when the rotor speed was dropped to 1/3. This nonlinear relationship between terminal voltage and driving rate produces a substantially constant load current and therefore, electric output over a wide speed range, at least under certain load conditions, inasmuch as the inductive reactance of the winding is proportional to frequency, and consequently, to rotor speed, so as to drop off more rapidly than the terminal voltage, in the event of a speed reduction, with a resulting improvement in the power factor of the load circuit. If the magnetic circuit contains only a single pole pair per air gap, the flux induced in the rotating armature will change its direction twice per revolution so that each revolution produces one complete cycle of 360 electrical degrees. In general, the number of electrical degrees per revolution will equal 360 times the number of pole pairs, it being apparent that this number ought to be odd since with even numbers it would not be possible to have poles alternating in polarity along the path of the armature and at the same time to have the north and south poles of each pair at diametrically opposite locations. In any case, it is important to dimension the curved facing faces of the pole pairs in such a manner so as to avoid allowing the armature to bridge between adjoining poles, so it is necessary to make the sum of the arcs spanned by these faces, in the plane of rotation, equal to considerably less than 360 degrees electrical. The invention will now be described in more detail, reference being made to the accompanying drawings in which Fig 1 and Fig 1a illustrate a first embodiment of my invention, shown in axial section and in a cross-sectional view taken on line IA of Fig 1 respectively. Fig 2 and Fig 3 are perspective views illustrating two other embodiments. Fig 4 and Fig 5 illustrate diagrammatically, two output circuit arrangements, one for a DC output and one for an AC output. Fig 6 is a somewhat diagrammatic illustration of an arrangement for comparing the outputs of a conventional generator and a generator according to this invention. The generator 100 shown in Fig 1 and Fig 1a comprises a stator 101 and a rotor 102 which has a pair of laminated armatures 102 and 102, carried on a shaft 103 which is free to rotate in bearings mounted in the end plates 104 and 104, of a generator housing 104 which is made from non-magnetic material, for example aluminium, which is rigidly attached to the stator. Shaft 103 is coupled to a source of driving power indicated diagrammatically by an arrow 110. The stator 101 includes a pair of yoke-shaped laminated electromagnets 101 and 101 whose extremities form two pairs of coplanar pole pieces, designated respectively 101A, 101B, north magnetic pole, and 101C, 101D, south magnetic pole. The pole pieces have concave faces, facing towards the complementary convex faces 102A, 102D of armature 102 and 102B, 102C of armature 102. These faces whose concavities are all centered on the axis of shaft 103, extend over arcs of approximately 200 to 250 each in the plane of rotation, Fig 1a, so that the sum of these arcs adds up to about 90. Geometrically and electrically, the stator magnets 101, 101 are surrounded by energizing windings 109, 109 which are connected across a suitable source of constant direct current, not shown. Similar windings, each composed of two series connected coils 106A, 106D and 106B, 106C, surround the rotor armatures 102 and 102, respectively. These coils form part of an output circuit which further includes a pair of brushes 107, 107 which are carried by arms 108, 108 on housing 104 with mutual insulation brushes 107, 107 cooperate with a pair of commuter segments 105, 105, see also Fig 4, which are supported by a disc of insulating material 105, mounted on shaft 103. By virtue of the series connection of coils 106A, 106D between the segments 105 and 105, as illustrated in Fig 4, the alternating voltage induced in these coils gives rise to a rectified output voltage at brushes 107 and 107. The unidirectional current delivered by these brushes to a load, not shown, may be smoothed by conventional means, represented by capacitor 112 in Fig 4. Fig 2 shows a modified generator 200, whose housing 204 supports a stator 201 essentially consisting of two permanent bar magnets 201 and 201, extending parallel to the drive shaft 203, on opposite side of it, each of these magnets being rigid and each having a pair of sole shoes 201A, 201C and 201B, 201D respectively. Rotor 202 is a pair of laminated armatures 202 and 202, similar to those of the previous embodiment, whose output coils 206A, 206B, 206C and 206D are serially connected between a slip ring 205, supported on shaft 203 through the intermediary of an insulating disc 205, and another terminal here represented by the grounded shaft 203 itself. Slip ring 205 is contacted by brush 207 on holder 208, the output of this brush being an alternating current of a frequency determined by the rotor speed. Fig 3 shows a generator 300 which is basically similar to the generator 100 shown in Fig 1 and Fig 1a. Its shaft 303 carries a pair of laminated soft iron armatures 302 which can rotate in the air gaps of a pair of electromagnets 301 which have windings 309 and 309. The commutator 305 again cooperates with a pair of brushes 307, only one of which is visible in Fig 3. This brush, carried on an arm 308, is electrically connected to a brush 313 which engages with a slip ring 314 positioned on an extremity of shaft 303 which also carries two further slip rings 315 which are in conductive contact with ring 314 but are insulated from the shaft. Two further brushes 316 contact the rings 315 and respectively are connected to windings 309 and 309. The other ends of these windings are connected to an analogous system of brushes and slip rings on the extremity of the opposite shaft, and arranged so that the two commutator brushes are effectively bridged across the windings 309 and 309 in parallel. Therefore, in this embodiment, the stator magnets are energized from the generator output itself, it being understood that the magnets 301 and 301, made, for example, of steel rather than soft iron, will have a residual coercive force sufficient to induce an initial output voltage. Naturally, the circuits leading from the brushes 307 to the windings 309 may include filtering as described in connection with Fig 4. Fig 6 shows a test circuit designed to compare the outputs of a generator of this design, such as the Unit 100 of Fig 1 and Fig 1a, with a conventional generator 400 of the type having a looped armature 402 which rotates in the gap of a stator magnet 401 which is fitted with energizing windings 409. The two generators are interconnected by a common shaft 103 which carries a flywheel 117. This shaft is coupled through a clutch 118 to a drive motor 111, which drives the rotors 402 and 102 of both generators in unison, as indicated by arrow 110. Two batteries 120 and 420, in series with switches 121 and 421, represent the method of supplying direct current to the stator windings 109, 109 and 409. 409 of the two generators. The rectified output of generator 100 is delivered to a load 122, shown here as 3 incandescent lamps connected in series, and with a combined consumption of 500 watts. Generator 400 provides current into an identical load 422. 2 watt meters 123 and 423 have their voltage and current windings connected respectively in shunt and in series with their associated loads 122 and 422, to measure the electric power delivered by each generator. When clutch 118 is engaged, shaft 113 with its flywheel 117 is brought to an initial driving speed of 1200 rpm. At which point, the switch 421 in the energizing circuit of the conventional generator 400, is closed. The lamps 422 light immediately and the corresponding watt meter 423 shows an initial output of 500 watts. However, this output drops immediately as the flywheel 117 is decelerated by the braking effect of the magnetic field on armature 402. Next, the procedure is repeated but with switch 421 open and switch 121 closed. This energizes generator 100 and the lamps 122 light up, watt meter 123 showing an output of 500 watts, which remains constant for an indefinite period of time, there being no appreciable deceleration of flywheel 117. When the clutch 118 is released and the rotor speed gradually decreases, the output of generator 100 is still substantially 500 watts at a speed of 900 rpm. And remains as high as 360 watts when the speed dropped further to 600 rpm. In a similar test with a generator of the permanent magnet type, such as the one shown at 200 in Fig 2, a substantially constant output was observed over a range of 1600 to 640 rpm. Teruo Kawai's COP=16 magnetic motor. In July 1995, a patent was granted to Teruo Kawai for an electric motor. In the patent, Teruo states that a measured electrical input 19.55 watts produced an output of 62.16 watts, and that is a COP of 3.18. The main sections of that patent are included in the appendix. In this motor, a series of electromagnets are placed in a ring to form the active stator. The rotor shaft has 2 iron discs mounted on it. These discs have permanent magnets bolted to them and they have wide slots cut in them to alter their magnetic effect. The electromagnets are pulsed with the pulsing controlled via an optical disc arrangement mounted on the shaft. The result is a very efficient electric motor whose output has been measured as being in excess of its input. James Hardy's self-powered water pump generator. There is a video on Google which shows an interesting self-powered water pump driven, electrical generator. At http://video.google.com.au/video play self-powered generator. This is a very simple device where the jet of water from the pump is directed at a simple water wheel which in turn, spins an electrical alternator, powering both the pump and an electric light bulb, demonstrating free energy. Initially, the generator is got up to speed, driven by the mains electrical supply. Then, when it is running normally, the mains connection is removed and the motor/generator sustains itself and is also able to power at least one light bulb. The generator output is normal mains current from a standard off-the-shelf alternator. James has patent application US 2007/00184611A1 published in 2007 on his design. In that application he points out that a major advantage of his design is the low noise level produced when the generator is running. In the video and the pictures above, the demonstration has the housing opened up in order to show how the generator system works, but during normal use, the compartments are completely sealed. In his document, James shows the overall system like this. The housing is divided into 3 separate compartments. The first compartment has a strong axle shaft running through it, supported on ball or roller bearings, possibly ceramic for this environment. The bearings are protected by being covered by splash guards which keep the water, or other liquid, off them. A water wheel of almost any type is mounted on the shaft, and a high-capacity water pump directs a stream of liquid onto the water wheel, striking the paddles at right angles in order to provide the maximum impact. This first compartment is sealed in order to contain all of the liquid inside it, and the bottom is effectively a sump for the liquid. A pipe located near the bottom of the compartment feeds the liquid to the pump, which is located in the second compartment. The pump boosts the liquid through a nozzle, directing it at the water wheel. While almost any nozzle will work, it is usual to choose one which produces a concentrated jet of liquid in order to generate the largest possible impact. One would expect that the larger the diameter of the water wheel, the more powerful the system would be. However, that is not necessarily the case, as other factors such as the overall weight of the rotating members might affect the performance. Experimentation should show the most effective combination for any given pump. The rotating shaft is given a third bearing supported by the side of the final compartment. The shaft then has a large diameter belt pulley mounted on it, the belt driving a much smaller pulley mounted on the shaft of the generator. This raises the rate at which the generator shaft is rotated. If the pump operates on AC mains voltage, then the generator will be one which generates mains voltage AC. If the pump operates on, say, 12 volts, then the generator will be one which generates 12 volts DC. The diagram above shows the arrangement for a mains voltage system, as that is probably the most convenient. If a 12-volt system is chosen, then the inverter can be omitted. The generator is started by pressing the normally open press button switch marked A in the diagram. This passes the battery power through to the 1 kW inverter, which then generates AC mains voltage. The switch marked B is a changeover switch, and for starting, it is set so that it passes the AC power through switch A to the pump. This causes the pump to turn on and direct a powerful jet of liquid at the water wheel, forcing it around and so powering the generator. When the generator gets up to full speed, switch B is flipped over, disconnecting the inverter and feeding the generator power through to the pump, keeping it running and supplying additional power to the output power sockets mounted on top of the housing. The press button switch is released, disconnecting the battery, which is no longer needed. Switch C is an ordinary on/off mains switch, which is needed if you want to turn the generator off. A major advantage of this generator system is that the main components can be bought ready-made, and so only very simple constructional skills and readily available materials are needed. Another advantage is that what is happening can be seen. If the pump is not working, then it is a simple task to discover why. If the generator is not spinning, then you can see that and sort the problem. Every component is simple and straightforward. James suggests that a suitable pump is the 10,000 gallons per hour torpedo pump from CalPump. Web site: http://www.calpumpstore.com/products/product details/part_number =T100000/416.0.1.1. Bill Muller's magnetic motor. Bill Muller, who died in 2004, produced a series of very finely engineered devices, the latest of which he stated produced some 400 amps of output current at 170 VDC for 20 amps at 2 VDC drive current. The device both generates its own driving power and produces an electrical power output. Bill's device weighed some 90 kilos, and it requires very strong magnets made of neodymium iron boron, which are expensive and can easily cause Serious injury if not handled with considerable care. It should be noted that Ron Klassen shows the details of his work in replicating this motor on his website, http://home.mchsi.com/act2/index.html, and he reports that he spent in excess of US $3,000 in construction and so far, has already achieved an output power of about 220% of the input power. A video of his motor in action is at http://video.google.com/videoplay?? Doc ID = 65862828639099378. And his development is progressing steadily. Ronald points out that decreasing the gap between the rotor and the stator by just 1 mm raises the input and output current by 10 amps, so the potential of his machine is 10 times greater than its present performance. Ronald has not implemented this as yet since the cost of the switching components is fairly high. His construction looks like this. The Muller motor has a lot in common with Robert Adams' pulsed permanent magnet motor. Both use a rotor which contains permanent magnets. Both pulse electromagnets at the precise moment to achieve maximum rotor torque. Both have pickup coils for generating an electrical output. There are, however, considerable differences. Bill Muller's coils are wound in an unusual way as shown below. He positions his rotor magnets off-center in relation to the stator coils. His coils are operated in pairs which are wired in series, one each side of the rotor. He has an odd number of coils and an even number of permanent magnets. His magnets are positioned with alternate polarity, N, S, N, S. In order to make it easier to follow, the diagrams below show just 5 coil pairs and 6 magnets, but much larger numbers are normally used in an actual construction of the device, typically 16 magnets. If AC mains voltage is used, then the drive wiring may be as shown here. When adapted for 5 pairs of coils, this becomes. If DC switching is used, then the circuit may be. This is an unusual arrangement made all the more peculiar by the fact that the drive pulsing is carried out on the same coils which are used for power generation. The driving power pulse is applied to every successive coil which, with just 5 coils, makes the drive sequence 1, 3, 5, 2, 4, 1, 3, 5, 2, 4. For this operation, coil 1 is disconnected from the power generation circuitry and then given a short high-power DC pulse. This boosts the rotation of the rotor. Coil 1 is then reconnected to the power generating circuitry, and coil 3 is disconnected and then given a drive pulse. This is repeated for every second coil, indefinitely, which is one of the reasons why there is an odd number of coils. The following table shows how the drive is operated. It is essential that neodymium iron boron magnets are used for this device as they are about 10 times more powerful than the more common ferrite types. Bill used 16 magnets in the 30 to 50 MGauss energy density range, constructed in China. They held their magnetism unaltered for 8 years of use. The air gap between the coils and the magnets is 2 mm. Bill used a computer chip to generate the switching sequence, and Ronald Klassen, who is expert in these systems, points out that the pulsing system is adjusted when the motor speed increases. This change is not a simple one, as when the speed of rotation reaches its maximum level, on a 16-magnet rotor, only 3 of the magnets would be driven by coils pulses. That is, during one rotation, just 3 electromagnets would be energized in one simultaneous pulse, and that pulse would be of longer duration than the pulses which accelerated to rotor from its stationary position. The output from each coil is passed through a full wave bridge to give DC, before being added to the output from the other coils. A typical Muller motor would have 16 magnets and 15 coil pairs. The solid coil formers were made from amorphous metal and are 2 inches, 50 mm, in diameter and 3 inches, 75 mm, long. Bill used a special mix of black sand, probably magnetite granules, encased in epoxy resin, but an alternative is said to be hard steel, the harder the better. The coil core material is said to be very important, and his construction was said to be free of any hysteresis eddy currents. The coils are wound from number 6 AWG, SWG8, or number 8 AWG, SWG10, wire and are formed in an unusual fashion as shown here. The winding turns are all made in the same direction. The first layer has 14 turns, the next 2 layers have 9 turns each, and the remaining 4 layers have 5 turns each, which gives a total of 52 turns. The coils are used in pairs, being wired in series, with one of each pair being on the opposite side of the rotor to the second coil of the pair, as indicated on the drawings. The way in which the coils are connected to the stator is not certain. The thin end of the coils face the rotor magnets. The pickup coils are not shown on the drawings, but they are placed on both of the stators, in every position where there is no drive coil. The rotor is constructed of non-magnetic material and spins at about 3000 rpm. This device has the potential to output 35 kW of excess power when constructed in the size described, which has a rotor diameter of 660 mm with the magnets centered on a circle of 570 mm. In the demonstration, which produced 35 kW of power, only 5 out of the intended 30 pairs of pickup coils had been constructed. It is predicted that the output would be 400 horsepower if all 30 pairs of pickup coils were in place. Predictions of this nature need to be borne out in a demonstration before they can be considered valid. Please be aware of the size of this item of equipment. I personally would not be able to pick up a device of this weight, but would need mechanical lifting equipment to move it. It can, of course, be constructed in a scaled down size which will have a scaled down electrical output. Let me stress that handling magnets of this strength has its dangers. Should you take a magnet in your hand and inadvertently move your hand near a loose steel item, then your hand is liable to become trapped between the magnet and the steel object. This may result in serious damage to your hand. Great care should be taken. The official website for this system is www.mullerpower.com, which you may find difficult to display unless you have the Macromedia software installed on your computer. The Rotoverter Power Amplification System. Not all pulsed drive systems use permanent magnets as part of their drive mechanism. For example, the Rotoverter, designed by Hector D. Perez Torres of Puerto Rico, and which has been reproduced by several independent researchers, producing at least 10 times more output power than the input power, uses standard 3-phase electric motors instead of magnets. This system has been reproduced by several independent researchers, and it produces a substantial power gain when driving devices which need an electrical motor to operate. At this time, the website http://panacea-bocaf.org/rotoverter.htm has considerable details on how to construct the device, as do the http://www.scribd.com/doc/2965018/high-efficiency FOR electric motors and the http://www.scribd.com/doc/263478117/rv-energy-saving-x documents. The outline details are as follows. The output device is an alternator which is driven by a 3-phase mains-powered, 3 HP to 7.5 HP motor. Both of these devices can be standard asynchronous squirrel cage motors. The drive motor is operated in a highly non-standard manner. It is a 240V motor with 6 windings as shown below. These windings are connected in series to make an arrangement which should require 480 volts to drive it, but instead, it is fed with 120 volts of single-phase AC. The input voltage for the motor should always be a quarter of its rated operational voltage. A virtual third phase is created by using a capacitor which creates a 90-degree phase shift between the applied voltage and the current. The objective is to tune the motor windings to give resonant operation. A start-up capacitor is connected into the circuit using the press button switch shown, to get the motor up to speed, at which point the switch is released, allowing the motor to run with a much smaller capacitor in place. Although the running capacitor is shown as a fixed value, in practice, that capacitor needs to be adjusted while the motor is running, to give resonant operation. For this, a bank of capacitors is usually constructed, each capacitor having its own on/off switch, so that different combinations of switch closures give a wide range of different overall values of capacitance. With the 6 capacitors shown above, any value from 0.5 microfarad to 31.5 microfarad can be rapidly switched to find the correct resonant value. These values allow combined values of 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, by selecting the appropriate switches to be on or off. Should you need a value greater than this, then wire a 32 microfarad capacitor in place and connect the substitution box across it to test higher values step by step to find the optimum value of capacitor to use. The capacitors need to be powerful, oil-filled units with a high voltage rating, in other words, large, heavy and expensive. The power being handled in one of these systems is large and setting one up is not without a certain degree of physical danger. These systems have been said to be self-powered, but this is not recommended, presumably because of the possibility of runaway with the output power building up rapidly and boosting the input power until the motor burns out. The Yahoo EVGRAY group at http://groups.yahoo.com/group/evgray has a large number of members, many of whom are very willing to offer advice and assistance. A unique jargon has built up on this forum, where the motor is not called a motor but is referred to as a prime mover or PM for short, which can cause confusion as PM usually stands for permanent magnet. Rotoverter is abbreviated to RV while DCPM-RV stands for direct current permanent magnet rotoverter, and TRUFO is a non-standard abbreviation for transformer. Some of the postings in this group may be difficult to understand due to their highly technical nature and the extensive use of abbreviations, but help is always available there. To move to some more practical construction details for this system. The motor, and alternator, considered to be the best for this application is the Balder M3770T 7.5 horsepower unit. The specification number is 07H002X790, and it is a 230/460 volt 60 Hz 3-phase, 19/9.5 amp, 1770 RPM, power factor 81, device. The Balder website is www.balder.com, and the following details should be considered carefully before trying any adaptation of an expensive motor. The following constructional photographs are presented here by kind permission of Ashwath of the EVGRAY group. The end plate of the drive motor needs to be removed and the rotor lifted out. Considerable care is needed when doing this, as the rotor is heavy and it must not be dragged across the stator windings, as doing that would damage them. The second end plate is then removed and placed on the opposite end of the stator housing. The fan is removed as it is not needed and just causes unnecessary drag, and the rotor is inserted the opposite way round to the way it was removed. That is, the housing is now the other way round relative to the rotor, since the rotor has been turned through 180 degrees before being replaced. The same part of the shaft of the rotor passes through the same end plate as before, as the end plates have also been swapped over. The end plates are bolted in position and the rotor shaft spun to confirm that it still rotates as freely as before. To reduce friction to an absolute minimum, the motor bearings need to be cleaned to an exceptional level. There are various ways of doing this. One of the best is to use a carburetor cleaner spray from your local car accessories shop. Spray inside the bearings to wash out all of the packed grease. The spray evaporates if left for a few minutes. Repeat this until the shaft spins perfectly, then put one, and only one, drop of light oil on each bearing and do not use WD-40 as it leaves a residue film. The result should be a shaft which spins absolutely perfectly. The next step is to connect the windings of the two units. The motor, the prime mover, is wired for 480 volt operation. This is done by connecting winding terminals 4 to 7, 5 to 8 and 6 to 9 as shown below. The diagram shows 120 volts AC as being the power supply. This is because the rotoverter design makes the motor operate at a much lower input than the motor designers intended. If this motor were operated in the standard way, a 480 volt three-phase supply would be connected to terminals 1, 2 and 3 and there would be no capacitors in the circuit. It is suggested that the jumpering of the motor windings is more neatly done by removing the junction box cover and drilling through it to carry the connections outside to external connectors, jumpered neatly to show clearly how the connections have been made for each unit, and to allow easy alterations should it be decided to change the jumpering for any reason. The same is done for the unit which is to be used as the alternator. To increase the allowable current draw, the unit windings are connected to give the lower voltage with the windings connected in parallel as shown below, with terminals 4, 5 and 6 strapped together, 1 connected to 7, 2 connected to 8 and 3 connected to 9. This gives a three-phase output on terminals 1, 2 and 3. This can be used as a three-phase AC output or as 3 single-phase AC outputs, or as a DC output by wiring it as shown here. The motor and the alternator are then mounted securely in exact alignment and coupled together. The switching of the direction of the housing on the drive motor allows all of the jumpering to be on the same side of the two units when they are coupled together, facing each other. The input drive may be from an inverter driven from a battery charged via a solar panel. The system how needs to be tuned and tested. This involves finding the best starting capacitor which will be switched into the circuit for a few seconds at startup, and the best running capacitor. To summarize, this device takes a low power 110 volt AC input and produces a much higher power electrical output which can be used for powering much greater loads than the input could power. The output power is much higher than the input power. This is free energy under whatever name you like to apply to it. One advantage which should be stressed, is that very little in the way of construction is needed, and off-the-shelf motors are used. Also, no knowledge of electronics is needed, which makes this one of the easiest to construct free energy devices available at the present time. One slight disadvantage is that the tuning of the prime mover motor depends on its loading, and most loads have different levels of power requirement from time to time. A 220 volt AC motor can also be used if that is the local supply voltage. If an alternator is being driven by the rotoverter motor, the prime mover, but although the shaft is being rotated rapidly there is no output voltage, then it is likely that the alternator has been sitting around unused for a long time and has lost the magnetic properties which it needs at startup. To fix this, connect each of the 3 output windings, one at a time, across a car battery for about 5 seconds to develop some magnetism, and the alternator will then work. This is a one-off thing only needed after a long period of inactivity. It is not essential to construct the rotoverter exactly as shown above, although that is the most common form of construction. The Muller motor mentioned earlier, can have a 35 kilowatt output when precision constructed as Bill Muller did. One option therefore, is to use one Balder motor jumpered as the prime mover drive motor and have it drive one or more Muller motor style rotors to generate the output power. Power boosting through coil short circuiting. The rotoverter output and the Muller motor/generator output, and possibly, the Adams motor output, can be increased very substantially by a technique developed by Cohn, the moderator of the EVGRAY Yahoo forum already mentioned. The technique is to place a dead short circuit across each output coil, just as the magnetic field of that coil reaches a maximum. This is done 5 times in rapid succession and can boost the output power by an estimated factor of 100 times. On the surface, it appears complete madness to place a short circuit across the very output which you are generating as the whole point of the exercise. However, it is not as mad as it seems. At the peak point, the coil itself contains a large amount of energy, and when a short circuit is placed across it, the result is quite unusual. The effect of short-circuiting an iron cord coil has been demonstrated by Ron Pugh of Canada with a bench test using this equipment. Here, a device for measuring magnetic fields is sensing the magnetic field of the coil as the rotor magnets move past the coil. The measurement is done with the coil operating normally and then again, with the coil short-circuited. The results are shown in these oscilloscope displays. Quite surprisingly, the magnetic field is reversed by the short circuit. If we consider just the first half of the cycle, you will notice that when the open coil has a very strong positive position, relative to a north magnetic pole, the short-circuited coil has a strong reading of the opposite polarity. Therefore, at any given instance near the peak, there is the potential for a major magnetic reversal if the coil were to be switched from the red area into the blue area and back again. You might imagine that if the coil short-circuiting were performed very rapidly, that there would be a result like this. However, this is not really possible with an iron core coil, as it is not able to reverse its magnetization rapidly enough to produce this effect. Coils with iron cores might get up to 3000 reversals per second, although 1000 would probably be a more realistic figure. For higher frequencies, a ferrite core could be used, and for yet higher frequencies again, an iron dust epoxy encapsulated core is needed. For unlimited frequencies, an air core coil is used. In the Rotoverter/Muller motor example, where Kohn has demonstrated major energy gains, the arrangement is different to Ron Pugh's bench test example. Firstly, the magnets on the rotor present two poles to the coil as they pass by, giving a full, even sine wave output. Secondly, Kohn uses an air core coil, and he has the fast switching implemented to take advantage of that coil type. This screenshot shows exactly the same effect, with the oscillating pulses plunging down to exactly where the negative trace would be at that time during each of the short-circuited periods. The display is showing a 20-volt peak-to-peak waveform, with each complete sine wave cycle taking 2 milliseconds. Instead of the original gradual magnetic rise to a single peak, there are now 5 very sharp magnetic reversals, each of which are substantially larger than the original peak. It is the change of magnetic flux in the pickup coil which produces the output power, so it can be seen that with this additional switching, a massive increase in flux change has been produced in the output coil. This increase is both a larger magnetic swing and a much greater rate of change of the flux, and as the rotor is spinning at some 1800 rpm and has many magnets in it, the overall magnetic power increases by a major factor. Please note that in the following diagrams produced by Kohn, the rotor magnet has a south pole which reaches the pickup coil first, followed by a north pole passing the coil. This produces an excellent sine wave output in the coil. The additional switching is performed by a mechanical brush and contact system, and the power collection circuit used for the short-circuited coil is. And when the coil is not short-circuited, the circuit is. Doug Konzen has been developing this circuitry and generously sharing his results freely. His website is at http://sites.google.com/site/alternative-world-energy/shorting-coils-circuits, and his most recent practical circuit is. There is a video on the web where coil shorting is used on the output from a replication of John Bedini's window motor. John's window motor is a cylinder with magnets mounted in it, spun inside a large coil by a pulsed motor. The motor can be a self-runner, but for the coil shorting demonstration, it was just spun briefly by hand, producing voltage pulses of about 16 volts. When the coil shorting is switched on, those pulses rise to about 440 volts, even though the coil shorting was not the optimum 5 times at peak, which would probably have raised the voltage pulses to about 1600 volts. The oscilloscope displays of the test shown on video are. I'm told that this coil shorting technique is used in industry but is considered to be a trade secret. Details of John Bedini's window motor can be found at http://www.fig-4-truth.com/schematics.html. Rahul Hadam's magnetic coupling system. Generally, the Rotoverter has very low input power when not loaded and about a 90% energy reduction when under load. The ideal situation is where there is a constant load, as the tuning of the Rotoverter does depend to some degree on the load. However, the rotoverter performance can be increased very substantially by using the techniques introduced by Rahul Hattam in 1955, which conventional science will not accept because according to current theory, any such energy gain has to be impossible and so, cannot happen no matter what evidence there is. Rahul Hattam's heretical statement is that using spinning magnets draws in energy from the environment, allowing a system to have COP1. Ever heard of John Searle's spinning magnet systems? His method is to use a motor, whether rotoverter or not, to spin a heavy rotor disc with 36 powerful rare earth magnets mounted on it. Then, using an identical heavy disc with magnets mounted on a generator to give a magnetic coupling between the motor and the generator can give not just coupling, but an energy gain as well. The heavy rotor provides some flywheel effect which helps with the operation of the system. Even with one motor as shown above, there is an energy gain as demonstrated in a recent video demonstration of the effect at http://www.youtube.com/watch?v=v-mqvzocnsi where a simple system produces 144 watts of excess power. However, the really big gains are got when several generators are driven by just the one motor. In passing, it may be remarked that there are two separate energy gain systems operating here. Firstly, the rotating magnetic field acts directly on the excess electrons in the local environment, drawing them into the system just as the fluctuating magnetic field of the secondary winding of any transformer does. Secondly, the rotors are receiving a rapid stream of drive pulses, and as Chas Campbell has demonstrated, that draws in excess energy from the gravitational field. Anyway, you will notice that the powerful magnets used have their north poles outwards on one rotor while the adjacent rotor has the south poles outwards. The very strong attraction between these opposite poles cause the generator disc to rotate in step with the motor disc. This process allows many generators to be driven by just the one motor as shown here and in the photograph above. For ease of drawing, the diagram above shows only 8 magnets per rotor disc, but you will notice in the photograph, and in the video, that there are 3 stepped rows of magnets on each rotor. You will also notice that direction of the stepping is reversed on every second rotor disc in order for the magnets to match each other in position as they rotate in opposite directions. While this type of arrangement gives a major increase in the output power compared to the input power, the situation can be further enhanced by retrieving some of the input power by means of electronic circuitry, and both Phil Wood and David Kusolides have kindly shared their methods for doing this. Phil Wood's Power Retrieval System. Phil Wood has many years of experience working with all varieties of electric motor, has come up with a very clever circuit variation for the rotoverter system. His design has a 240-volt prime mover motor driven with 240-volt AC. The revised circuit now has automated startup and it provides an extra DC output which can be used to power additional equipment. His circuit is shown here. Phil specifies the diode bridges as 20 amp 400 volt and the output capacitor as 4000 to 8000 microfarads 370 volt working. The on/off switch on the DC output should be 10 amp 250 volt AC working. The circuit operates as follows. The charge capacitor C needs to be fully discharged before the motor is started, so the press button switch is pressed to connect the 1K resistor across the capacitor to discharge it fully. If you prefer, the press button switch and resistor can be omitted and the switch to the DC load closed before the AC input is applied. The switch must then be opened and the AC connected. The starting capacitor S and capacitor R both operate at full potential until capacitor C begins to charge. As capacitor C goes through its charging phase, the resistance to capacitors R and S increases and their potential capacitance becomes less, automatically following the capacitance curve required for proper AC motor operation at startup. After a few seconds of runtime, the output switch is operated, connecting the DC load. By varying the resistance of the DC load, the correct tuning point can be found. At that point, the DC load resistance keeps both of the capacitors R and S operating at a potentially low capacitance value. The operation of this circuit is unique, with all of the energy which is normally wasted when the AC motor is starting, being collected in the output capacitor C. The other bonus is where a DC load is powered for free while it keeps capacitors R and S in their optimum operating state. The DC load resistance needs to be adjusted to find the value which allows automatic operation of the circuit. When that value has been found and made a permanent part of the installation, then the switch can be left on when the motor is started, which means that it can be omitted. If the switch is left on through the starting phase, capacitor C can be a lower value if the DC load resistance is high enough to allow the capacitor to go through its phase shift. The capacitor values shown above were those found to work well with Phil's test motor, which was a 3-winding, 5 horsepower, 240 volt unit. Under test, driving a fan, the motor draws a maximum of 117 watts and a variable speed 600 watt drill was used for the DC load. The motor operates at its full potential with this circuit. The circuit will need different capacitors for operation with a 120 volt AC supply. The actual values are best determined by testing with the motor which is to be used, but the following diagram is a realistic starting point. The 120V AC motor runs very smoothly and quietly, drawing only 20 watts of input power. Advancing the design even further, Phil has now produced an extremely clever design by introducing an additional DC motor/generator coupled to the prime mover motor. The coupling is nominally mechanical with the two motors physically linked together with a belt and pulleys, but the electrical linking is such that the two motors will synchronize automatically if the mechanical linkage is omitted. I should like to express my thanks to him for sharing this information, diagrams and photographs freely. This circuit is very clever as the DC motor/generator automatically adjusts the running of the AC motor both at startup and under varying loading. Also, the selection of the capacitors is not so critical and no manual intervention is needed at startup. In addition, the DC motor/generator can be used as an additional source of electricity. Phil setup. As the loading on the prime mover motor is quite low due to the very high efficiency of the rotoverter arrangement, it is perfectly feasible to drive the whole system with a low-power inverter run from a battery. If that is done, then it is possible to use two batteries. One is charged by the DC generator while the other is driving the inverter. A timer circuit then switches the batteries over on a regular basis using relay switching. David Kusolide's power retrieval system. A very effective additional circuit has been developed by David Kusolides. This circuit allows extra current to be drawn off a rotoverter while it is running, without increasing the input power needed to drive the rotoverter. David's circuit can be used with a wide range of systems, but here it is being shown as an addition to the rotoverter system, raising its efficiency even higher than before. As is common with many effective circuits, it is basically very simple looking, and its apparent operation is easily explained. The objective is to draw additional current from the rotoverter and use that current to charge one or more batteries, without loading the rotoverter at all. The current takeoff is in the form of a rapid series of current pulses which can be heard as a series of faint clicks when fed into the battery. Let us examine the circuit section by section. First, we start with a standard off-the-shelf three-phase motor. In this example, the motor is a 7.5 horsepower motor, which when wired in rotoverter mode, using just a single-phase supply as shown here, only draws a very low amount of power when running, especially if the single-phase supply is about 25% of the voltage rating of the motor. Because the running power draw is so low, it is possible to run this motor from a standard battery-powered inverter, but the current draw at startup is some 17 amps, so the mains is used to get the motor started and then the motor is switched from the mains to the inverter. The inverter also allows easy measurement of the power input and so makes for easier calculation of the overall power efficiency of the system. There is a power extraction device called a diode plug, which in spite of its seeming simplicity, is actually much more subtle in its operation than would appear from a quick glance at the circuit. This circuit has been presented as a public domain non-copyrightable circuit by Hector Perez Torres and it is capable of extracting power from a range of different systems, without affecting those systems or increasing their power draw. In the circuit presented below, just the first half of the diode plug is utilized, though it should perhaps be stressed that it would be perfectly feasible to raise the efficiency of the circuit even further by adding extra components to duplicate the power feed from the battery, drawing on both parts of the diode plug circuit. For clarity, this is not shown here, but it should be understood that it is a possible, and indeed desirable, extension to the circuitry described here. When the motor is running, high voltages are developed across the windings of the motor. As only the first half of the diode plug is being shown here, we will be capturing and using the negative going voltages. These negative going pulses are picked up, stored in a capacitor and used to charge a battery using the following circuit. Here we have the same rotoverter circuit as before, with high voltage being developed across capacitor C1. The battery charging section is a free-floating circuit connected to point A of the motor. The high voltage diode D1 is used to feed negative going pulses to capacitor C2, which causes a large charge to build up in that capacitor. At the appropriate moment, the PC851 opto-isolator is triggered. This feeds a current into the base of the 2N3439 transistor, switching it on and firing the 2N6509 thyristor. This effectively switches capacitor C2 across the battery, which discharges the capacitor into the battery. This feeds a substantial charging power pulse into the battery. As the capacitor voltage drops, the thyristor is starved of current and it turns off automatically. The charging sequence for the capacitor starts again with the next pulse from the windings of the motor. The only other thing to be arranged is the triggering of the opto-isolator. This should be done at the peak of a positive voltage on the motor windings and has been built like this. Here, we have the rotoverter motor as before, with the voltage developed on C1 being used to trigger the opto-isolator at the appropriate moment. The voltage on C1 is sensed by the diode D2, the preset resistor VR1 and the resistor R1. These place a load of some 18 k ohms on capacitor C1 as the neon has a very high resistance when not conducting. The 10-turn preset resistor is adjusted to make the neon fire at the peak of the voltage wave coming from the motor. Although the adjustment screw of most preset resistors is fully isolated from the resistor, it is recommended that adjustment of the screw be done using an insulated main tester type of screwdriver, or a solid plastic trimmer core adjustment tool. The circuit to test one half of the diode plug is then. The switch SW1 is included so that the charging section can be switched off at any time, and the switch should not be closed until the motor gets up to speed. All wire connections should be made before power is applied to the circuit. Capacitor C1, which is shown as 36 microfarads, has a value which is optimized for the particular motor being used and will normally be in the range 17 to 24 microfarads for a well-prepared motor. The motor used for this development was retrieved from a scrapyard and was not prepared in any way. The value of capacitor C2 can be increased by experimenting to find at what value the resonance gets killed and the charging section starts drawing extra current from the supply. It should be noted that many new thyristors, silicon-controlled rectifiers or SCRs, are faulty when supplied, sometimes as many as half of those supplied can be faulty. It is therefore important to test the thyristor to be used in this circuit before installing it. The circuit shown below can be used for the testing, but it should be stressed that even if the component passes the test, that does not guarantee that it will work reliably in the circuit. For example, while 2N6509 thyristors are generally satisfactory, it has been found that C126D types are not. A thyristor passing the test may still operate unpredictably with false triggers. Please note that the 2N6509 package has the anode connected inside the housing to the metal mounting. Tab. Components list. 1 k ohm resistor 0.25 watt 3 bands, brown, black, red. 2 k ohm resistor 0.25 watt 1 bands, gray, red, red. 10 k ohm preset resistor 110 turn version. 4.7 MF440V, or higher, capacitor 1 polypropylene. 36 MF440V, or higher, capacitor 1 non-polarized polypropylene. 1N5408 diode 1. 1N4007 diode 1. 2N3439 NPN transistor 1. 2N6509 thyristor 1. Several may be needed to get a good one. PC851 opto-isolator 1. Neon, 6 mm wire ended, 0.5 mA 1 radio spares 586, 015. 5A fuse and fuse holder 1 any convenient type. 30A switch 1 pole 1 throw 1 toggle type, 120 volt rated. Veroboard or similar 1 your preferred construction board. 4-pin DILIC socket 1 black plastic opto-isolator holder, optional. Wire terminals 4 ideally 2 red and 2 black. Plastic box 1 injection molded with screw down lid. Mounting nuts, bolts and pillars 8 hardware for 8 insulated pillar mounts. Rubber or plastic feet for any small adhesive feet. Sundry connecting wire 4M various sizes. When using and testing this circuit, it is important that all wires are connected securely in place before the motor is started. This is because high voltages are generated and creating sparks when making connections does not do any of the components any particular good. If the circuit is to be turned off while the motor is still running, then switch SW1 is there for just that purpose. The operating technique is as follows. Before starting the motor, adjust the slider of the preset resistor VR1 to the fixed resistor end of its track. This ensures that the charging circuit will not operate as the neon will not fire. Power up the circuit and start adjusting the preset resistor very slowly until the neon starts to flash occasionally. There should be no increased load on the motor and so no extra current drawn from the input supply. If there is an increase in the load, you will be able to tell by the speed of the motor and the sound it makes. If there is an increase in the load, then back off VR1 and check the circuit construction. If there is no increased load, then continue turning VR1 slowly until a position is reached where the neon remains lit all the time. You should see the voltage across the battery being charged increase without any loading effects on the motor. If you use an oscilloscope on this circuit, please remember that there is no ground reference voltage and that the circuit is not isolated. Here is a picture of David's actual board construction. There are various ways for building any circuit. This particular construction method uses plain matrix board to hold the components in position and the bulk of the interconnections are made underneath the board. The charge collecting capacitor is made here from 2 separate polypropylene 440 volt capacitors wired in parallel. David has opted to use a separate diode on each capacitor as this has the effect of doubling the current carrying capacity of a single diode and is a popular technique in pulse charge circuits where sometimes several diodes are wired in parallel. David has included a heatsink, which he marks as being not required, but you will notice that there is insulation between the SCR and the heatsink. Mica washers available from the suppliers of semiconductors are particularly good for this, as mica is a good insulator and it also conducts heat very well. A thyristor, SCR, testing circuit. The components needed to construct the thyristor testing circuit shown below can be bought as kit number 1087 from www.quasarelectronics.com. The circuit is operated by operating SW1 several times so as to get capacitors C1 and C2 fully charged. LED 1 and LED 2 should both be off. If either of them light, then the thyristor is faulty. Next, with SW1 at its position 1, press switch SW2 briefly. LED 1 should light and stay on after SW2 is released. If either of these two things does not happen, then the thyristor is faulty. With LED 1 lit, press SW3 and LED 1 should go out. If that does not happen, then the thyristor is faulty. As mentioned before, even if the thyristor passes these tests, it does not guarantee that it will work correctly in any circuit, as it may operate intermittently and it may trigger spuriously when it shouldn't. Component list: 47 ohm resistor 0.25 watt 1 bands, purple, yellow, black. 470 ohm resistor 0.25 watt 2 bands, purple, yellow, brown. 1K ohm resistor 2 bands, brown, black, red. 100 mF 15V capacitor 2 electrolytic. 1N914 diode 4. Light emitting diode 2 any type, any size. Toggle switch 2 pole 2 throw 1. Press button push to make 2 non-latching press on, release off type. 9V battery 1 any type. Battery connector 1 to match chosen battery. Socket 1 plug-in socket for thyristors. Veroboard or similar 1 your preferred construction board. Plastic box 1 injection molded with screw-down lid. Mounting nuts, bolts and pillars 8 hardware for 8 insulated pillar mounts. Rubber or plastic feet for any small adhesive feet. Sundry connecting wire 4 meters various sizes. Philwood second power retrieval system. Philwood has developed a particularly effective method for extracting the excess resonant circulating energy of a rotoverter prime mover. This is the circuit. Care needs to be taken when constructing this circuit. For example, the circuit performance is displayed by an HEF4017B 5-stage Johnson counter, but for some lunatic reason, the 4017 designation is also used for a completely different chip of the same size and number of DIL pins, namely the CMOS high-speed hex flip-flop with reset, an action definitely worthy of a stupidity award. Another point to watch out for is that the 1A1N5819 diode is a very high-speed Schottky barrier component. The circuit operation is as follows: the input from the rotoverter motor is stepped down by a transformer to give an 18-volt, nominal, AC output, which is then rectified by a standard rectifier bridge and the output smoothed by an 18-volt Zener diode and a 330mF smoothing capacitor, and used to power the MC34151 chip. This DC power supply line is further dropped and stabilized by a 15-volt Zener diode and a 47mF capacitor and used to power the LED display chip HEF4017B. The rotoverter input is also taken direct and rectified by a second 400-volt 35-amp rectifier diode bridge and smoothed by a 20mF capacitor with a high voltage rating. It must be understood that the rotoverter system is liable to produce considerable power surges from time to time, and so the circuit must be capable of handling and benefiting from these surges. This is why the IRG4PH40UD IGBT device was selected, apart from its very reasonable price, as it robust and can handle high voltages. The resulting high voltage DC is taken by the chain of components 275-volt Zener diodes, 20K resistor and the 100K variable resistor. The voltage developed on the slider of this variable resistor is loaded with a 10K resistor and voltage limited with a 10-volt Zener diode, and decoupled with a 10NF capacitor before being passed to the MC34151 high-speed MOSFET dual driver chip. Both of these drivers are used to sharpen up the pulse and drive the IGBT cleanly. The result is an output which is a series of DC pulses. The operation of the circuit can be seen quite clearly, thanks to the HEF4017B display circuit, which drives a row of LEDs, triggered by the IGBT gate signal, divided by the 1K/47K voltage divider decoupled by the 10NF capacitor. This display shows clearly when the IGBT is switching correctly. Actually, the display circuit is quite a useful device for people who do not own an oscilloscope, not just for this circuit, but a wide range of different circuits. The physical board layout for Phil's circuit is shown here. As you will notice from the notes on Phil's board layout shown above, the first of the 75-volt Zener diodes used on the direct rotoverter power feed should be replaced with a 30-volt Zener if a 120-volt motor is used in this circuit. Another important point which needs to be stressed is that the pulse DC output from this circuit can be at extremely high voltages and needs to be treated with considerable care. This is not a circuit for beginners, and anyone who is not familiar with handling high voltages needs the supervision of an experienced person. Also, if either this circuit or the rotoverter is connected to the mains, then no scope ground leads should be connected, as the circuit can be 100 volts or more below ground potential. The pattern of the printed circuit board when viewed from the underside of the board is shown here. and component packaging is. Phil's build of his circuit was implemented like this. Component list. 10 ohm resistor 0.25 watt 1 bands, brown, black, black. 100 ohm resistor 0.25 watt 2 bands, brown, black, brown. 1 kilo ohm resistor 0.25 watt 2 bands, brown, black, red. 2.2 kilo ohm resistor 0.25 watt 1 bands, red, red, red. 4.7 kilo ohm resistor 0.25 watt 1 bands, purple, yellow, red. 10 kilo ohm resistor 0.25 watt 1 bands, brown, black, orange. 22 kilo ohm resistor 0.25 watt 1 bands, red, red, orange. 10 nanofarad capacitor 3. 5 microfarads 440V, or higher, capacitor 1 polypropylene. 20 microfarads 440V, or higher, capacitor 1 polypropylene. 47 microfarads 25V capacitor 1. 330 mF 25V capacitor 1. 1N5819 Schottky barrier diode 1. 10 volt Zener diode 1. 15 volt Zener diode 1. 18 volt Zener diode 1. 75 volt Zener diode 2. 400 volt 40A rectifier bridge 1. 35 volt 1A rectifier bridge 1. MC34151 IC1. HEF4017B IC1. IRG4PH40 UD transistor 1. LEDs 10 any type or alternatively, and LED array. 100K ohm variable resistor 1. Plastic knob for variable resistor 1. 240. 18 volt mains transformer 1 150 mA or higher rated. 10A switch 1 pole 1 throw 1 toggle type, 120 volt rated. Veroboard or similar 1 your preferred construction board or PCB. Wire terminals 4 ideally 2 red and 2 black. Plastic box 1 injection molded with screw down lid. Mounting nuts, bolts and pillars 8 hardware for 8 insulated pillar mounts. Rubber or plastic feet for any small adhesive feet. Sundry connecting wire 4 meters various sizes. Lorentz Ziehungskopf equal 3 pulsed flywheel. Lorentz has been presenting his theory of lead-out energy, which indicates that excess energy is drawn from the environment when there is an impact. The method of producing this effect which he has followed is to create an unbalanced wheel and demonstrate that excess energy is produced. It should be stressed that energy is never created or destroyed, and so, when he measures more energy in his device than the energy which he uses to power it, energy is not being created but is instead being drawn in from the local environment. Lorentz has recently demonstrated a prototype to members of the public. This simple device was demonstrated to have 3.3 times as much output power as the input power needed to make it operate. This is an early prototype which was demonstrated in October 2009, and Lorentz and his helpers are working on to produce more advanced models which have kilowatts of excess electrical power. Mr. Ziehung remarks, the Ziehung lead-out energy theory was first disclosed to the world on 20th December 2004 at Tai-Po, in Hong Kong. The lead-out energy theory basically says that one can lead out, or bring in, energy from the surrounding environment into a lead-out energy machine. The total input energy is equal to the sum of the supplied energy plus the lead-out energy. For example, if the supplied energy is 100 units and the lead-out energy is 50 units, the device's total input energy will be 150 units. This means that the output energy can be more than the supplied energy of 100 units provided by the person using the device. If we ignore the small loss of energy caused by less than 100% efficiency of the device itself, then the output energy will be the whole of the 150 units. If we use 50 of the output energy units and feed back 100 of the output units as the supplied energy, then that supplied energy can again lead out another 50 units of excess output energy for us to use. Thus a lead-out energy machine can continuously lead out pollution-free, virtually inexhaustible and readily available energy for us to use. We do not need to burn any fossil fuel or pollute our environment. The two examples of lead-out energy which we access are gravitational and electron motion energy. The lead-out energy theory does not violate the law of conservation of energy. The law of conservation of energy has been used as a roadblock for the so-called over-unity devices. The patent offices and the scientific establishment routinely dismiss an invention as belonging to the impossible perpetual motion machine category if the inventor cannot identify the energy source of his invention. We got the help of Mr. Tong Po Chi to produce a 60 cm diameter lead-out energy machine in October 2009. The output energy of that device is greater than the input energy by a factor of 3 times. These results are confirmed by voltmeters and ammeters measuring the input and output energies. The Tong wheel has been shown at 2 open shows in Hong Kong, Inno Carnival 2009 and Inno Design Tech Expo, in November and December 2009. Over 25,000 people have seen it. The Better Hong Kong radio show has video recorded it, the discussions being conducted in Chinese. At this time, the Tong wheel is at the radio studio available for experts to view and examine with their own instruments. The Tong wheel has a diameter of 600 mm and this large size is considered to be important. It has 16 permanent magnets mounted on its rim and 15 air core coils mounted around it on the stator. There is one position sensor. The coils can be switched to act as drive coils or as energy collection coils. With this arrangement, if the positions the switches as shown for 10 of the 15 coils shown here, then they act as drive coils. The sensor is adjusted so that the drive circuit delivers a brief energizing pulse to those coils just after the magnets have passed their exact alignment position with the coils. This causes them to generate a magnetic field which repels the magnets, thrusting the rotor around. The pulse is very brief, so very little power is needed to accomplish this pulsing. As mentioned before, any number of coils can be switched to provide this driving force. With this particular wheel construction by Mr. Tong, the best number has been found to be 10 drive coils. The power pickup is achieved by gathering the electricity generated in some of the coils as the magnets move past them. In this particular arrangement, 5 of the coils gather energy while 10 provide the drive. For the sake of simplicity, the diagram shows the 5 collection coils adjacent to each other, and while that would work, the wheel is better balanced if the drive coils are evenly spaced out around the rim. For that reason, this switching would actually be selected to give 5 sets of 2 drive coils followed by 1 pickup coil, as that gives a perfectly balanced thrust on the wheel. The 2 diagrams above are shown separately in order to make it clear how the drive switching and the power pickup switching are arranged. The full design arrangement and the balanced switching are shown in the following diagram, which indicates how the full design is implemented on this particular implementation of the wheel design. The sensor can be a coil feeding a semiconductor switching circuit, or it can be a magnetic semiconductor called a Hall effect device which can also feed a semiconductor circuit. An alternative would be a reed switch, which is a simple mechanical switch encased in an inert gas inside a tiny glass envelope. Suitable switching circuits are described and explained in Chapter 12 of this e-book. Mr. Tsiung remarks that the large wheel size is due to the fact that the pulse force takes time to impart the impulse to the wheel and lead out energy from the environment into the system. If you want to see this actual wheel, you can email Dr. Alexandra Yuan at ayuan@hkstar.com to make an appointment. The Tong wheel is located at the Better Hong Kong radio studio in Causeway Bay, Hong Kong. Just say that you want to see the lead-out energy machine. The demonstration can be in English or in Chinese. Ideally, there should be a group of at least 6 visitors, with 1 or more being a qualified engineer or scientist, and you are welcome to bring your own cameras and or test equipment. It is planned to produce a version which has a 300-watt output, and another with a 5 kilowatt output. Educational kits are also planned. If you decide to replicate this particular design, then to raise the output power level you might consider putting another set of coils around the wheel and either using them as 15 additional energy pickup coils, or alternatively, pulsing the wheel twice as often. Adding one or more additional rotor discs to the same rotating shaft is also an option, and that has the advantage of increasing the rotor weight and improving the effect of the impulses on the rotor. The diameter of the wire used to wind the coils is a design choice which has a wide scope. The thicker the wire, the greater the current and the larger the impulse given to the wheel. The coils are normally connected in parallel as shown in the diagrams. Because of the way magnetic field strength drops off with the square of the distance, it is generally considered good design practice to make the coils 1.5 times as wide as they are deep, as indicated in the diagrams above, but this is not a critical factor. This design is, of course, a version of the Adams motor described at the start of this chapter. Although motors of this kind can be built in many different ways, the construction used by Mr. Tong has some distinct advantages, so here is a little more detail on how I understand the construction to be carried out. There are two side pieces which are attached together by 16 cross timbers, each of which are held in place by 2 screws at each end. This produces a rigid structure, while the construction method is as simple as is possible, using readily available materials which are worked with the most basic of hand tools. The construction also allows the motor to be taken apart completely without any difficulty, transported as a flat pack package and then assembled at a new location. It also facilitates people who want to see the motor taken apart after a demonstration in order to assure themselves that there is no hidden power source. Each of the cross timbers provide a secure mounting platform for an electromagnet and its associated switch. In the implementation by Mr. Tong, there appears to be just the one rotor, configured as shown above with 16 permanent magnets mounted in its rim. The magnetic poles of these magnets are all orientated in the same direction. That is to say, the magnetic poles facing outwards are all either south or all north poles. It is not critical whether the outward-facing poles are north or south, as Robert Adams used both arrangements with great success, but having said that, most people prefer to have the north poles facing outwards. Robert has always said that one rotor was enough, but his techniques were so sophisticated that he was able to extract kilowatts of excess power from a single small rotor. For us, just starting to experiment and test a motor of this type, it seems sensible to stick with what Mr. Tong has experienced success. However, this build by Mr. Tong is not his final motor but just one in a series of continuously improved motors. The following diagram shows an arrangement which has 3 rotors attached to a single shaft, and while you may choose to construct this with just one rotor, if the cross timbers are long enough, then 1 or 2 extra rotors can be added in very easily at a later date. Here, just 2 of the cross timbers are shown. The electromagnet coils used by Mr. Tong are air core, as that type have the least effect on the passing magnets. However, electromagnets with cores tend to be much more power for any given current flowing through them. In theory, the core should be made of lengths of insulated iron wire, as that would reduce power loss through eddy currents flowing in the core, but Robert actually recommends solid metal cores, and as he was the most experienced person in this field, paying attention to what he said seems sensible. The core material needs to be a metal which magnetizes easily and powerfully, but which does not retain any of its magnetism when the current stops flowing. Not many metals have those characteristics, and soft iron is usually recommended. Nowadays, soft iron is not always readily available, and so a convenient alternative is the central bolt of a masonry anchor, which has excellent properties. The shaft of the bolt can be cut quite easily with a hacksaw, but be sure to remove, or file down, the head of the bolt, as the increase in diameter has a marked effect on the magnetic properties of the electromagnet core if it is left in place. The bolt shown above is a M16X 147 mm masonry anchor bolt with a bolt diameter of 10 mm. Some makes of drying felt whiteboard markers have a rigid body which fits the 10 mm bolt exactly and provide an excellent tube for constructing an electromagnet bobbin. With a core in the electromagnets, the rotor gets additional rotating power. Initially, the magnets on the rotor are attracted to the electromagnet cores, giving the rotor a turning force which does not require any current to be supplied. When the rotor magnets are at their closest point to the electromagnet cores, the windings are powered up briefly and that gives the rotor magnets a strong push away, causing the rotor to spin. There are many different designs of simple drive circuits and it is probably worth trying out different types to see which works best with your particular build of motor. In the same way, there are many kinds of collection circuits for taking off some of the excess power generated. The most simple of these is just a diode bridge, perhaps feeding a battery and charging it up for use at a later time. If you get sophisticated with the collection circuit and just take power off for a very short period of time at the correct moment, the cutting off of the current draw causes a back EMF magnetic pulse in the collection electromagnet which causes it to give the rotor an extra drive push, both current collection and rotor drive in one combined package. Here are two of the most simple circuits possible, one for drive and one for power collection. The drive circuit transistor is switched on by a voltage generated in the gray coil by a rotor magnet passing by. The transistor then feeds a large current pulse to the black coil, driving the rotor on its way. The neon and the diode are there to protect the transistor, and a physical layout for the circuit might be: the 1K variable resistor is adjusted to give the best performance and the on/off switch is optional. More advanced circuits, such as the one on page 2 to 9, can also be tried and the performance compared. Generally speaking, I would expect a 3-rotor version to give a better performance than a single rotor implementation, but experimentation is needed. Mark Wessling's generator proposal. A proposed generator design put forward by Mark Wessling has the promise of particularly high performance. This is presented here as an idea, as this device has not yet been built as far as I am aware. Mark calls this the infinity motor/generator. In this design, the rotor drive is achieved through the use of 4 or more independent small high-speed motors, each mounted on the main rotor and each provided with its own smaller rotor as shown below. An open source project to build, test and refine this device is at http://www.overunity.org.uk/show-thread.php?mark759-the-motor-hyphen-the-hyphen-motor-hyphen-generator-motor-hyphen-P=29540 where a video of the basic operation of the device is shown. Seen from the front, the rotors are positioned like this. The magnets are mounted very securely in the small rotors so as to be sure that they cannot break loose when the rotor spins at high speed. The drive mechanism for the main rotor is unusual in that it uses the Lenz's law drag effect. There is a ring of power pickup coils positioned so that when the magnets of the small rotors are in the position farthest from the main rotor axle, they are directly facing the coil as shown here. This has very little effect until an electric current is drawn from the coils. When that happens, the Lenz's law drag opposes the movement of the magnet. But, as the moving magnet is effectively mounted on the large rotor, that opposing push drives the large rotor in the opposite direction. If the small rotors spin in a clockwise direction, then the large rotor will be driven in a counterclockwise direction. Surprisingly, the greater the current draw, the greater the rotation rate of the large rotor. It is envisaged that the spin rate of the large rotor may become excessive, so in order to slow it down while producing additional output power, the main rotor shaft is extended and an ordinary magnet/coil generator arrangement attached to it. While initially, each 9-volt motor has been shown with its own separate battery, there is no particular need for the motors to be 9-volt, and a more convenient arrangement is where all 4 motors are fed power from a single source, using 2 insulated slip rings mounted on the axle with spring-loaded brushes pressing against them as shown here. This drawing omits 2 of the small rotors and their motors in order to show a possible slip ring and brush arrangement. Each experienced constructor has his own idea as to the optimum spacing between magnets on a rotor and a set of power pickup coils. The different types and strengths of the magnets used in different implementations of this design also has an effect on this spacing. The very experienced New Zealand experimenter and inventor, Robert Adams, has found that spacings around half an inch, 12 mm, can give optimum performance. Other builders are of the opinion that the space between the magnet and the coils should be the minimum possible. To allow for experimentation to find the optimum spacing, it is suggested that the construction should allow for the gap between each set of magnets and their associated coils to be adjustable. To allow for this, the style of construction shown here might be considered. With this arrangement, wing nuts are used to allow easy adjustment of the position of the coils. The slip ring on that side of the axle needs to be much wider to allow this change of position without affecting the power feed through the slip ring. Mark has advanced his idea further and is in the process of constructing a prototype. His more advanced method uses cylindrical magnets which are magnetized along the axis of the cylinder. One such magnet is this one from http://www.magnet4less.com/index.php?cpath=1_133:. The design uses 8 small DC motors with unloaded speed of 8,000 rpm, mounted on the rotor, each with one of these magnets mounted on the motor drive shaft, as shown here. The other power collection methods remain the same as shown previously. The coils shown for this latest suggestion are air core, but what works best has to be determined through experimentation. The magnets are rotated very rapidly by the motors, perhaps 2500 rpm, and each revolution causes a field reversal at the motor drive shaft. The magnets are powerful, so there should be a considerable effect on the coils, and it only takes a 30-degree rotor movement to move from being exactly over one coil to being exactly over the next one, and there will be considerable magnetic effect in the intervening positions as well. Mark comments on this arrangement: the main rotor will spin at just a few hundred rpm. This will pull the electrons forward through the coil, as opposed to a conventional coil that pushes the electrons. This action will pass the lens force onto the main rotor shaft as torque. The beauty of this design is that it puts the motor shaft in the same phase as the rotor spin, whereas before, it was 180 degrees out and slowed the motors. Also, the gyroscopic forces on the small rotors/motors were great as the large rotor spun, while this design will hit every coil 100% on every rotation. The technique of coil shorting 5 times at the sine wave peak can boost the output power by anything up to 100 times, so using that method would be a major benefit if the necessary electronics skills are available. The coils shown appear to have a solid core, however, it is envisaged that the speed of rotation will be too great for a ferrous core, and so either ferrite or air core coils may be needed. Art Porter's magnetic system. Art uses an electromagnet with a ring magnet mounted on the core. When the coil is pulsed so as to augment the field of the permanent magnet, Art says that his prototype produces 2.9 times the field strength of the permanent magnet on its own. When the coil is pulsed in the direction which opposes the field of the permanent magnet, the resulting magnetic field is zero. This is a very serious change of magnetic field which can be used in different applications. One which Art has implemented is using the arrangement to power a crankshaft motor. Art shows several different motor builds including this one. With this arrangement, Art states that 95% of the motor power comes from the permanent magnet. Art's website is at http://www.gap-power.com/index.html, and he has a very interesting, lengthy video showing all of the details at http://www.gap-power.com/videos/full%20 length%20 video.wmv. In the video, Art attempts to apply Ohm's law in an attempt to analyze the operation and is puzzled when the oscilloscope readings do not match his Ohm's law calculations. He thinks that there is a contradiction between the oscilloscope and Ohm's law, which he repeatedly stresses is a law of nature, and he concludes that one of them has to be wrong. In actual fact, neither are wrong because Ohm's law only applies to DC current flow in resistive circuits, and Art is not using steady DC current or a resistive load. Applying short DC pulses to a substantial coil of wire is the equivalent of applying AC to that inductor. Ohm's law does not apply due to the inductance of the coil. There is a power factor involved and back EMF voltage pulses, so the oscilloscope readings are what is needed to calculate the input and output powers. This arrangement is almost identical to that used in the Charles Flynn magnet motor described in Chapter 1, and very close to the techniques used by Robert Adams in a properly tuned Adams motor as shown at the start of this chapter. In my opinion, the effect which Art is exploiting would best be used if a large pickup coil is placed against the end of the electromagnet core and the drive coil pulsed at the coil's high resonant frequency, as that will minimize the input power and maximize the output power. Stacking those units in a bank could well produce a very sizable excess electrical output. Our thanks are due to Art and his colleagues for sharing their research work freely for others to replicate and progress further.